Hi everyone, let's get started. This is the video recording for Lecture 16 of Engineering 111. Of course, just as a reminder, if you found this video, then you know we're not having an actual physical class on Thursday, March 2nd. We're doing this virtually, but we will be back to our normal schedule on Tuesday. So I'll see you in person on Tuesday, March 7th. A couple of reminders. First of all, for this lecture, there's going to be a section towards the end of the recording where you need to follow along and prepare a histogram. Please upload that Excel file that you prepare to MU Online to receive participation credit. And the other thing to keep in mind is that your homework assignment number 5 is due by 11 o'clock on Tuesday, March 7th. So we won't have any in-person meetings between the time that that homework assignment is assigned to you and when it's due. I think it's relatively straightforward, but if you do have questions, please feel free to send me an email and I'll do my best to respond. In today's class, what we're going to be discussing is just some general information about statistics, which engineers use a lot and is really important. We're going to be briefly identifying how you can import text data into Microsoft Excel, and then talking about and generating a histogram. So just to lay the groundwork for statistics, we need to draw a contrast between two different types of processes and numbers, deterministic and stochastic. Now, a deterministic process is something where the outcome of the process is always perfect and it's exactly a certain number. As an illustration of that, consider if you have an angle of exactly 60 degrees and you put it into the cosine function, then what comes out of that cosine function is the number 0.5 with perfection. And no matter how many times you put that into your calculator, if you put that into your calculator 100 times, you'd get 0.5 as the output each time. There would never be any difference because it's a deterministic process where there cannot be variation. Now that's kind of isolated in the real world. Mathematics is one of the few things that has that perfect, unvarying perfection. But in the real world, we have far more commonly stochastic processes. And that is that there's some sort of randomness that finds its way into the process. And so consider manufacturing as an illustration. If you put raw stock of, let's say, a bar of metal into a computer-controlled lathe, then what comes out will be a finished product like a drive shaft of a car, for instance. It's going to be pretty close to 0.5 inches in diameter, but it's not going to be exactly 0.5 inches in diameter. Some parts, maybe because the cutting surface of the lathe got dull, maybe then they would be larger than they should have been. Maybe if there was an earthquake while the lathe was running, then the shaft would have some imperfections to it. There can be a lot of factors like the lubricating oil changes its properties, and so the point is in the real world, the output of any kind of a process has some uncertainty. Like it may have an average size, but then there are going to be some that are too big, some that are too small. So as another illustration, consider a loaded semi-truck. And even if it's being measured with a scale and loaded to capacity, like trucks I think are supposed to have a maximum capacity of about 80,000 pounds. So if you load that truck up to 80,000 pounds, scales aren't 100% accurate. They may be slightly out of calibration, and so then the actual truck weight may be varying a little bit from that 80,000 pound target, where some are overweight and some are underweight. So those are just two illustrations of how in the real world we have variations from a central tendency, and those variations are interesting to study and sometimes can be very important. We have to be careful about statistics, though. Here's a quote from Benjamin Disraeli, who was the Prime Minister of the British Empire. And Mark Twain quoted him as saying that there are three kinds of lies: lies, damn lies, and statistics. So, of course, that's implying that statistics can really be used in a sinister way if somebody wants to. You can misquote or misinterpret statistics, and so they can be very useful in understanding the reality of the situation, or they can be twisted to kind of promote ignorance or to promote an unrealistic understanding of what's actually going on. Here are some terms, that some definitions of statistics. It can be defined as a branch of applied math. It can be a statistic, can be defined as a numerical quantity that's characterizing a population, or statistics can be the analysis of variation. So it can be used as a noun, as an adjective, or as a verb, like statistical analysis. So statistics, we have to kind of understand the limitations in order to use it appropriately. It's an important tool, but all tools can be potentially misused if the people don't know what they're doing or are being intentionally malicious. Probably the first thing that people learn when they're studying statistics is the idea of the average, sometimes more technically referred to as the mean. So assume that you have a population of, it could be of anything. It could be a classroom full of people, and if you're measuring their age. The way that you would determine the average age is by simply adding each of the parameters together and then dividing by however many samples there were, how many different people were in the population. So here that formula is saying that you add up the value from the first to the last, and then you divide by the number of measurements that were taken in order to quantify the mean. Mean can be thought of as maybe the typical value or the most likely value, but that can be misconstrued, and we're going to look at a couple of different illustrations of these numbers just to give some insight into how statistics could potentially be misused. So let's say that you have 20 people in a classroom, and you record the ages, and then when you do that formula of you adding them together and dividing by 20, it comes out that the average age is 21. So knowing that the average age is 21, what would you say about that population? Would you say it's a college class, a high school class, a middle school class, or grade school? And most of us would think it's probably a college class, right? Okay, that may be. We'll look at the data in just a minute. Now what about in the case of same 20 people, but that's a different 20 people, but the number's the same. And this time when we calculate the mean age, it's 12 when rounded to the nearest year. So in this case, is that a college class, high school class, middle school, or grade school? Okay, so let's actually look at the data just to analyze what's going on here. Now in the first case, we were talking about the average age was 21. Consider group 1. If you look at all of the ages there, that does appear to be a college class. The college level class have an average age of 20.6. But now what is this group 2? Some of them 30 years old, 10 years old, 32 and 9, 32 and 8. When you take the average is very close to what it was in group 1, but it turns out that group 2 was actually a population of people who were attending a PTA meeting, where some of them were young kids attending with their parents. And so this was, all of them were about the same age. Here the group could be described as bimodal, meaning that some of them are young, some are old, but the average age is actually kind of not as relevant at describing who's really in the audience. So this is an illustration of how you have to be careful by relying on just one statistic to describe a population. The same thing is true here in group 3. We remember we were saying it was 12-year-olds, and that might have made you think that that was a class of middle school students. But in reality, it's a kindergarten class, because we have a lot of very young students between 5 and 7 years old, and then a pair of teachers who are in their 60s that raise the average age to 12. And so, you can do the same thing with people's net worth. If you look at the net worth of the graduating class where Bill Gates went to high school, you'd think, wow, all those people are millionaires, but really you've got one billionaire and a bunch of ordinary people that are throwing off the average. Here are histograms that illustrate those previous 3 data tables. And so histograms are useful at visualizing the data, and it's showing, for example, that you have a group of people where the age is pretty close together. Here is the bimodal distribution where you have young children and older adults. And then in group 3 you had very young children and a pair of older teachers. And so sometimes a visual representation of a statistical summary can be even more valuable than the raw data, just because the answer of what's going on jumps out at you more clearly. So we've talked about average, which is also referred to as the mean. Another measure of central tendency is the median, and median is the middle value in a population. And if you ordered it from highest to lowest or from lowest to highest, the value that's in the middle, that's the median. If you have an odd number of items, then it's easy to just pick out the median because it truly is in the middle. But if you have an even number of items, you have to take the average of the two that are closest to the middle. So if you have one central value, then that divides the entire population of data into two parts, those that are above the median and those that are below the median. You could also figure out the quartiles, which is in the middle, the upper 25%, the bottom 25%, and so then you have the population divided into 4 groups. Deciles would be when you find the value that corresponds to the upper 10%, and then the 10 to 20%, and so on. Here are those same 3 groups with their ages sorted from smallest to highest. And since this is an even number of people, it was 20, in order for us to calculate the median, we have to take the average of the two middle. And so in the case of the high school students, the median age is 20 because we have a pair of 20-year-olds that are on either side of that middle line. In the case of group 2, which was the PTA meeting, the median includes 1 elementary school student and 1 parent. And so then it gives us a median age of 19.5 when we take the average of those two values. But here now in the case of the kindergarten class, since what's in the middle is a pair of 6-year-olds, then the median is completely unaffected by the fact that you have a couple of older teachers in the classroom. These teachers could have been 500 years old, and that median age would still be 6. If they were 500 years old, then the average age would have changed considerably. And so sometimes it's helpful to have both the median and the average available in order to give you a clearer idea of what's actually happening. Okay, so there's yet another way of measuring the central tendency, which means what's going on with the middle of a population, is the mode, which is you're trying to count up what is the value that occurs the most often, so with the greatest frequency. Ordering the data from lowest to highest is another thing that helps you identify the mode because all of the like numbers occur at the same time. So that just makes it a bit easier to count them. Now, if the data is around the average, then the mode and the mean may be exactly the same. But there are some times where the mode and the mean are pretty different. So remember, I've already used the phrase bimodal to describe that group of people who were at the PTA meeting because there were some of the young students and some of the parents as well. So consider here where we've sorted the data from lowest to highest, and then we count to see which is the value that occurs most often. In the case of the college class, the mode is 19 because there are 6 people who have the age of 19, and none of the other ages have more than 6 people in that age. In the case of group 2, the most frequently observed age is the age of 9, and that happened 5 times. And so now here's a wild difference between mode and then the median and the average. So we have to be careful with the mode, and if you were only interested in what age is there the most of in that PTA group, you'd say, well, there was mostly 9-year-olds. then that wouldn't really tell you a lot about the population. But in the case of the kindergarten students, the mode was age 6. That was what's there most frequently, which also happens to be the same as the median. So these are all, in different circumstances, useful ways of describing the central tendency of a population. So we've talked about the average, which is the mean, the mode, and median. And those are all measures of the central tendency, which you can think of kind of as like the typical member of a population or a sample of a population. But another way of looking at data is how spread out it is from that central tendency. And what this figure is illustrating is variance. Variance is a quantitative way of measuring how dispersed the data is from the central tendency. Here in red, it's showing that most of the values are pretty close to whatever this middle point is. You know, there are a handful of people who are getting a little bit less and a handful of people who are getting a little bit more, but it's tightly clustered around the central tendency, and so that means there's low variation. In the case of the blue line, though, you'll notice that there is still a central tendency, but more of the people are further away from the central value. And so that's an illustration of a population that has high variance. If you want to calculate variance, then that is calculated according to the formula here. Now, this isn't a formula that I would expect you to memorize necessarily, but you can use it as a function in Excel using STEV, standard variation, and the P is meaning for a population. Now, it's important for me to tell you that a population means all of the people in a group. So if you have, for example, 60 students in a statics class, and you wanted to find out the variance of their scores on an exam according to STEV.P function, then you'd use all of the scores. But sometimes what people will do, because it's difficult to measure an entire population, for example, during political races, they won't call every person in America and ask them who they're going to vote for. But instead what they'll do is they'll ask just a sample, like a representative sample. So maybe they would choose 200 people at random and measure something about those 200 people. So here is the way of measuring the variance according to just a sample of a population. Now the formula here is a little bit more complicated because it's including both the sample size, and if you have one of the sample data points, you want to measure how far away it is from the mean. So X bar is the mean or the average value, and so you're finding out the difference between one person and the average. So if we were talking about scores, it would be your score minus the average score. And you do that for all of the people inside of the sample from 1 to n, where n is the number of people included in the sample, and you're squaring the difference between the two and then dividing that by n minus 1. If you're applying the function in Excel, then STEV, standard variation, .s, and the s is indicating to Excel that it's a sample and not the entire group. The standard deviation is sometimes a statistic that gets thrown around, and it represents the distance away from the average, where on either side of one standard deviation, 68% of the population should lie. 68%. And so here's a figure that illustrates that nicely. Here's the bell curve that we've already seen once today when we were looking at high variance versus low variance. So a bell curve is just saying that if you have some average value, most of the people will be pretty close to the average value, but the further away you get from the average, there are going to be fewer and fewer people. So think about how quickly could people run a mile. You know, maybe the average would be 10 minutes. There are going to be a handful of people that can run that mile in 4 minutes. Not very many. Maybe more who could run it in 5, even more who could run it in 8 minutes. But then at the low end, there may be some people who take 45 minutes to run a mile. And so how close together that grouping is described by the standard variation. The standard deviation is sigma, and it is showing you within one standard deviation of the average, there should be 34% of the people on one side and 34% on the other. Deviation is, this difference is what we saw inside of the formula for variation just a moment ago. It's how different one value is from the average value. And deviation plots can sometimes be used to find out how far away people are from the average and whether there's a wide scattering or whether most of the people are pretty close to the mean. Okay, so that's it just as the basic stuff on statistics for now. We will come back to it later. But what I wanted to demonstrate is how you can open file types other than .xlsx, which is the standard file type that's used by Microsoft Excel. First of all, I wanted to mention that about 10 years ago, they switched from XLS to XLSX. And the reason for that is XLSX is more of an open source format that's, I guess, also compressed. And so occasionally you might run across older spreadsheet files that just have XLS and they open immediately in Excel. You know, there's a backwards compatibility that makes opening them seamless. But I just wanted to point out the difference that this is the old file extension and this is the newer file extension. And I think that transition happened maybe in 2007 or 2010. What can sometimes be a little bit more challenging are data files with the appendix .csv and .txt. So .csv are comma delimited data files, and you can sometimes find these files on like government websites that have data like stream flow data or weather data. And so let's try opening up a .csv file. Okay, I've got a .csv file here. It's called cylinder test data. And to open it up, you'll notice that it's already associated with Microsoft Excel. So if I double click on it, then here's data that opens immediately. Now, one thing we have to be cautious about is as long as it's saved as .csv, then I'm not able to include a lot of information that normally could go along with Microsoft .xlsx file. So for example, let's say that I created a graph of some data. I'm going to select these values. I'm just throwing together a chart really quick just so that we have a chart. Okay, here's the X data, and then here's some Y data. All right, so the point is we've got data, and now if I went to save this file, if I just click the save button, it's going to give me a warning. And what it says is that some of the features may be lost if you save it as the .csv. And so do I want to keep using that format? If I said yes and it saved my work, now I'm going to close it. It'll give me that warning again because it's so nervous about me losing some of what I've created since I've been using the program. It says, do you want to save it? So I already did. I haven't made any changes since I saved it, so don't save. And so now if I look at here, it shows it was just updated, and so I can open it again, but my graph's gone. And so the point is .csv is not a file format that will retain all of the features. It's just for the data itself. And so when you open up a .csv, what you ought to do as a very first step is save as, to make sure that now you're going to change the file type to Excel, and then cylinder test data, and then maybe just to further distinguish it with graph. And this time, if I made some sort of a graph, then saved it, then it's going to keep that. Okay, so here's some data. Ooh. All right, and my values here. All right, so if I save that file and close it, okay, here's the one that I made with the graph, and you'll notice that now, yes, it's there. So that's the thing I wanted to tell you about .csv. Now, Microsoft Excel isn't the only thing that could open up a .csv. If you right-click on it, then it'll allow you to choose what to open it with. And if I opened it just with the notepad, we can look at what that data actually is. And what it actually is numbers in the parentheses here, and then commas. CSV means comma delimited. And so these commas are an indication to Microsoft that it needs to create a new column. So each one of these each one of the commas, so it's saying this number's in a column, and then put in a new column. That's what the comma means. And the reason why these numbers are in quotes is they don't want that to trigger it to tell it to put it in a new column. So if those quotations weren't there, then that comma would be making Excel think to create a new column. So it's a way of getting around it. Now you notice how this is saying sample number, comma, 2-day break, comma. It's sort of like sticking further to the right, but it doesn't actually create the columns based on the position on the page. It's going to still think that sample number goes into the first column as that. Even though the words are wider, it doesn't start looking for the next column's worth of information until it sees that comma. Now a similar thing is going to be true with this data file here that says cylinder test data.txt. Now .txt isn't normally associated with Microsoft Excel in the same way that the .csv was. If I just double click on that file, it's going to open it up into the notepad, and you can see here now this is formatted slightly differently. In this case, those commas aren't there to tell it that there should be a new column, but there are some additional spaces. And so rather than opening it directly, we're going to have to import into Excel. So if I start opening Excel here, and I tried to open it directly, I'm going to browse to the location of where that file is saved, and I won't even see it. I know that that file is in that folder, but it's not showing up right now. And the reason is down here, you're filtering which file types to show. And right now it says only show the Excel file types. And so if I click on that, it's going to bring up a list of different types of files that it can open. And I could tell it to show me .txt, text files, but it's just easier just to say all files. Show me everything that's in that folder. And so now we see the cylinder test data. So when I go to open it, it's going to prompt me to go through a little wizard that asks questions about making sure the data is imported correctly. And the options here, delimited and fixed width. Delimited is telling Excel to look for some sort of a characteristic to trigger a new column. So if we go to next, then it will give you a preview of what the data is going to look like. And here it's saying use a tab as the indication that you have a new column's worth of data. If I took that off, then it would import the data all screwed up. So let me try that. See, all the data it's in the same column. So this, I wouldn't be able to do any calculations with this. I imported it wrong. So let me close it and try importing the data again in a different way. So let me browse to the location. I'm going to open the cylinder test data, and this time I'm going to delimit, but I'm going to tell it, yes, leave tabs as the delimiter, and then finish, and here the data looks fine. I may need to adjust the column widths a little bit to see all of the words, but they're there. And of course, just the advice I gave you before to save your work as a different file type, I'm going to change from text over to an Excel workbook, and then everything would be fine. I could start putting in graphs and calculations, and all of those features would be saved. So that's all I really wanted to show you about importing text files. The final thing that we're going to talk about today are histograms. And probably you've seen figures like this before. What it is it's showing you how many trees there are in a certain height range. You can see what we're saying is from 65 to 70 feet, then there are 4 trees that have that height characteristic. From 70 to 75, there are 2. From 75 to 80, there are 9, and so on. So this kind of chart is called a histogram, and it is useful because it shows you more than just the average would. You know, if we took the average, I guess we can paste that data into Excel in a moment and find out what is the average, but it will tell you whether the data is clustered around a central value or whether it's bimodal. That is a visual representation of the clustering and the grouping. And so what we need to do is create what are called bins, and those are the groupings for the data. Here's the raw data itself, and what I'd like you to do, you need to upload a file today for attendance and participation credit, and the file that I'd like you to upload is the one related to creating this same histogram. And you can find the starting point data as a file in MU Online. Okay, so the file that's going to be available in MU Online is this trees.txt. So you're going to get practice importing a text file and also creating a histogram. So the first thing you should do is in Excel, I'm going to close this and start from scratch. So File, Open, Browse, and I'm going to open up trees. If you don't see the trees as an option, then it's probably because you have it set to only show Excel files right now. So change the file type so that it's showing you all files, and then there you can open the trees.txt. And it will give you this text import wizard. In this case, there's only one column of data, so it's probably going to be just fine to import it however you like. So just click Finish, and there it is, our tree height, and it's in feet. Now what we want to do is create bins, and so let's put this in, bins, and the grouping is going to be, we want to measure everything up until 65 feet, and then from 65 to 70 feet. Make that a bit bigger. Okay, from 70 to 75, 80, 85, and 90. Now, the tool that you need to use to do this probably isn't available on your version of Excel right now. So I think what you're going to need to do is turn it on in the same way that you may remember we had to turn on the solver as an add-in. If you go to File, Options, and then the add-ins, there is, to manage in the add-ins, we want to turn on the Analysis Tool Pack. The Analysis Tool Pack is, it has a tool called the Histogram tool, and that's what we're going to use to create our figure. So turning on the Analysis Tool Pack is going to add a new feature over here on the Data tab that wasn't there before. You see here where it says Data Analysis. If you don't turn on the add-in, you're not going to see Data Analysis on the Data tab. So now we've turned it on, and there it is. So I'm going to click Data Analysis, and there's a whole list of different types of data analysis it can do. What I'm most interested for this point is creating a histogram. Okay, so it will take me through a little wizard and ask some questions here for the histogram. First of all, it wants to know where is the data. So I'm going to select the range of cells that has the underlying data in it. So there's my data. Okay, and then my bin is going to be these numbers that are the cutoff points. Now it wants to know where to put the data. Should it put the output of the analysis on the same worksheet? And if I wanted to do that, then I just do this, and I'd click the location that I wanted the report. Or you can have it create a whole new worksheet tab down here. So that's what this is, new worksheet client. And then I could call it histogram. It can also automatically create the chart for you based on the analysis that it does. And what's kind of interesting sometimes to see is the cumulative percentage. It's a curve that it will put on top of the histogram. So let's enable both of those as we click OK. So you'll notice it created a new tab. Now if we haven't already, what we need to do is be sure to save our work. So let's do a save as, because right now it's just the text file, and we need to change it from text to an Excel workbook. And so this is going to be spreadsheet file for 3-2. All right, so we've got that saved. Now, if the computer crashes, we still have our work. So here's the histogram that it created, which looks exactly like what we want. Over here on the left axis, it's including the frequency, which corresponds to those bars. On the right axis is the cumulative percentage. And so here it's showing that in the first bin, which was from 0 to up to, and also including 65, then there are 4 trees. And so you can see that the cumulative percentage eventually reaches 100%. Now, just as a matter of personal preference, let's change the formatting. Here it's giving us 120.00%. Well, I don't need to see that 0.00, so I'm going to change the number here to 0 as the decimal places, and that makes the figure a little bit easier to see. What if we wanted to add the labels on? So if you click on this and then click the plus button, we could also have on data labels, and then it will tell you how many are in each group, which is kind of nice. And if we wanted to make this a bit bigger, then it would make it easier for us to change the size of, change the size of some of those. So I could change it from 10 to maybe 14, and then the font isn't going to be so small. I could change the name of this to Tree Heights on Shady Lane. Okay, so if you've been following along, then you've created your first histogram. Be sure to save the file and then upload this file to MU Online as evidence that you participated in today's class meeting. As we finish, let's take a look. Oh, and the place to upload that, it's called 3-2. So that stands for March 2nd, which is the date of our lecture. That's where you should upload the file to. Concluding with a last look at the announcements here, please keep in mind that you need to upload the file, otherwise you won't get attendance credit for this lecture. And then also homework 5 is due by 11 o'clock on Tuesday the 7th of March.